Okay, we're going to continue our study of the open book test 3334. Question number 5 says, find the points of inflection. Now, the first questions we asked were the critical points. And when you look for critical numbers, we want to do a little bit of review here. What do we do to find critical numbers? So we take the first derivative of the function and set it equal to 0. We want to know whether the first derivative is equal to 0 or undefined. And what could possibly be at a critical number? A relative maximum, a relative minimum, or a point of inflection. So there's possibly a point of inflection at a critical number. And we think about, well, how am I going to know whether there's a point of inflection or if it's a maximum or minimum? Well, the way we studied that is we looked at the intervals, right? And so we would have divided, with those critical numbers, we would have divided it out into intervals, right? And if in this particular interval, the first derivative was positive, that told us it was increasing. And if in this interval it was negative, it told us that it was decreasing. So we thought if it's going from increasing to decreasing at that place right there, then it must have been a relative maximum. Okay. Or if it went from if this interval was positive, and we said, okay, it's positive so that it is increasing again, we would say, well, it's going from decreasing to increasing, so at that critical point there must be a relative minimum. And then we said if we had an interval and it went from increasing to increasing, then we would have had a situation maybe like that, where at that point it was still increasing. It went from increasing to increasing, and so it changed concavity at a certain point. So therefore, at that point that it changed concavity, we call that a point of inflection. Now, something that's important at that point that I wanted to bring out in our little discussion here, when we're thinking concave up and down, we're thinking about pieces of a concave up parabola and pieces of a concave down parabola. So let's just kind of do this. The idea I want you to get is that those two parabolas are going to intersect in how many points? Exactly 1 point. And that point is the point of inflection. And so here's the idea. The idea is, to the left of that point of inflection, we have a bunch of points, an infinite number of points that are concave up. And to the right of that point of inflection, we have an infinite number of points that are concave down. But at that point of inflection, we have neither. We have neither. It's neither concave up or concave down at that 1 point. Well, at that 1 point, how do we know if it's concave up? If the second derivative is positive, and we know that it's concave down if the second derivative is negative. Well, how do we know where the point of inflection is? It's where the second derivative is 0, okay? Now, we can know where a point of inflection is with the first derivative test by seeing that at that point it went from increasing to increasing or decreasing to decreasing. But with the second derivative test, we can find where there's a point of inflection by seeing where the second derivative is 0. Okay, so there's all of our rules kind of put together as we go through this. So the question here is, find the points of inflection. Well, and then discuss concavity. Well, it's actually the second derivative that will allow us to quickly find where it's concave up, concave down, or there's a point of inflection. We can find the point of inflection with first derivative, but it's not as easy as it is with second derivative. Okay, so what we want to do is find the second derivative. So we'll have f prime of x is 4 times 2 is 8x, and then reduce the exponent by 1, 8x to the third, and then good minus 8x. And then the derivative of 0 of 3 is 0.
The x goes away.
The x goes away. Yes.
The derivative of x
We
is
get
1.
it. Derivative of x is 1. That's right. So, minus 8. Thank you. See, I said y'all to be here to help me when I make blunders. I'm glad you're here. Okay, and then we want to do the second derivative. So, in the second derivative, we're going to have 24x to the second, and the derivative of a constant goes out 0. Okay? So, the second derivative is 24x squared. Now, we could find a test point, a point where things are going to change, or concavity is going to change, or a point of inflection, which would be when what? When the second derivative is equal to 0, we have a point of inflection. To one side of that point of inflection, there would be one type of concavity, and to the other side of that, there would be another type of concavity. So we can create test intervals for concavity by finding what we call test points in the second derivative. In the first derivative, we would have called it a critical number, so we need to call it something else. We're going to call it a test point. So we're going to divide by 24. And then we would have x squared is equal to 0. And then we're going to take the square root, and we're going to get x equals 0. So at x equals 0, there's a test point. Okay? Now, we could say, well, we could go further and talk about concavity. We could say, okay, let's create some test intervals with that. We could say if I go from negative infinity to 0, 0 to positive infinity, then that's going to be my test intervals. And I could try to find out what the concavity is within that point, within that region. So, if I take the second derivative of a point within the left interval, I can just choose a -1. Or if I took the second derivative of a number within the second interval, then I can just take a +1. And I'm going to plug those into my second derivative. So I'd have -1 squared is 1 times 24 is 24. And so it's a positive 24. That means that it is, we're on second derivative. Second derivative talks about concavity, not increase, decrease. So first derivative gives us increase, decrease. Second derivative gives us concave. So concave up, very good. Concave up. It's easy to let all that get away from you. I'm dropping little derivatives, things I'm supposed to know, and I got the other part. It's easy to mix up your first and second derivatives, so that's study with that. Okay, when you plug in a +1 over here in place of x, you still get the same thing, positive 24. So this is also positive, so it's concave up. So the idea is that it's going from concave up to concave up. It's going from a concave up situation to a concave up situation. Right? It appeared that, okay, my second derivative, I have a 0. I set it equal to 0, and so we would say, well, at that point is a possible point of inflection, but it never changed concavity. To the left of that point, it's concave up. To the right of that point, it's concave down. So that point 0 is not a point of inflection at all. Okay? It appears to, if it's going from concave up to concave down, to be a minimum or a maximum. So we would say that the graph, it never changes concavity, therefore it is not a point of inflection. Okay? it never changes concavity. Therefore, there is no point of inflection. So where the graph, where the second derivative is positive, it's concave up. Where the second derivative is negative, it's concave down. Where the second derivative is 0, there is a possible point of inflection. A possible point of inflection. We can see what that point is. When x is 0, if we go back to our original function, right? Those would 0 out, and we would have f of 0 is 3, so that would be the point 0, 3. And if we graphed that, we would maybe think that there's a minimum there maybe. Let's look at the graph of that just to investigate. I think it's worth going to the graphing calculator there. So let me pull up the graphing calculator. Okay, so we've got our graphing calculator opened up. We're going to plug in that equation. It was 4x squared, I believe, 4x squared, and then 2x. It was 2x to the 4th. Fun. It was 2x to the 4th. There we have it. Okay, minus 8x minus 8x plus 3. Okay, so let's just hit graph and take a look at what that looks like. That's nice. I didn't get all that stuff figured out. Okay, so we're going to hit graph, and you can actually see the graph there. I'm going to go to second trace, which is calculate. I'm going to calculate the minimum, number 3. I'm going to do a left bound, and then I'll do a right bound, and enter. And then I'll just kind of get in the middle of that. Hit enter. And what we can see graphically there is there's actually a minimum at negative 3. What was going on at that 0 positive 3, as we would have known as an x-intercept. So it's not a minimum, it's not a maximum, but it's also not a point of inflection, because it's a part of a concave up picture on this side of it, and it's a part of the concave up picture on that. The entire graph, you can see, every point on the entire graph is a part of a concave up situation. Okay. So we found a place where the second derivative was 0, but it ended up not necessarily being a point of inflection because there was no change in concavity in the graph. Okay, any questions on that? All right, so we'll go back to question number 6. All right, so we determined concavity. As we discussed, it says discuss the concavity and the point of inflection. So for number 5, we would say it's concave up on the entire graph, therefore there's no point of inflection. That's the idea that we got. So we would want some kind of discussion about that. Okay, so let's look at number 6. We want to talk about concavity and points of inflection. So we want to work our way to the second derivative, and we want to think about what's going on in those intervals and whether in a certain place there's a change in concavity, therefore a change in a point of inflection. So let's do the derivative. We're going to take the first derivative. So we have the derivative of sum. The derivative of x is 1. Now remember, the derivative of cosine is negative sine, right? But we have that constant 2. So we have 1 times, and 1 plus, excuse me, 1 plus. And then we're going to have 2 times the derivative of the cosine, which is negative sine, so the negative could pop there on the 2 sine x, right? So plus negative 2 sine x. And then when we do the second derivative, the derivative of the constant goes out. Now the derivative of sine x is cosine x, so our sign doesn't change here, so now we're going to have negative 2 cosine x. So there's my second derivative. Now it does give us an interval, right? And we want to set that equal to 0, so we have negative 2 cosine x is equal to 0. We're trying to find test points for the second derivative. And test points will give us possible points of inflection, right? Where the second derivative is 0, there's possibly a point of inflection, but to actually be a point of inflection, there has to be a change in concavity at that point, okay? So, we're going to solve here, so we're going to get the junk off of cosine, so we would divide by negative 2, and we'd have cosine of x is 0. Now, we're thinking again to the unit circle, and we know that we're going from 0 all the way around to 2 pi, and we're thinking in our mind the cosine of, the cosine of how many degrees is 0. So the cosine of what is 0? Well, the cosine of pi over 2 is 0, and then again at 3 pi over 2. Very good. Quadrantal angles. So x is equal to pi over 2, or x is equal to 3 pi over 2 are our test points, right? And from those test points, we could create intervals, test intervals for the second derivative. So we'd have negative infinity to pi over 2, pi over 2 to 3 pi over 2, and from 3 pi over 2 to positive infinity. So we can check for concavity using the second derivative and points of inflection. Again, each of those points, the pi over 2 and the 3 pi over 2, are possible points of inflection. That's the points at which second derivative was 0, but they can only be a point of inflection if there's a change of concavity at that point. Okay, so we need to choose something within that first interval that we have memorized, right? So we want something between negative infinity and pi over 2, but we have to be between 0 and pi over 2, so we're really choosing something from 0 to pi over 2, right? We really aren't going from negative infinity because my limit is 0, right? If I put in my limits, and this over here is really not positive infinity, it's really 2 pi because I'm limited by the interval that we're bound into. So between there, what's something that you know that's a pretty little number? Well, because pi over 3 is 60, and the cosine of 60 is 1/2, so we know that's a pretty little number. So if I were to say, okay, I want the second derivative of pi over 3, then we would determine, well, it's in the first quadrant, so everything's positive, so it is a positive 1/2. Now, we're more concerned with that it's positive, and the fact that it's positive means that it's concave up.
What do you have to multiply by -2? It's the second derivative.
You're right. Thank you. You're keeping me straight. We've got to plug this. We've got to plug our, let me start again. We've got f double prime of pi over 3, and we have to plug that in here. So we have a -2 times that. Thank you. So we have a -2 times the positive 1/2 that we talked about, which is a -1. And so it's negative, therefore it is concave down. Very good. eyes on the focus. Now, between pi over 2 and 3 pi over 2, between pi over 2 and 3 pi over 2 is in this area. And what's something that we've got memorized easy there? Pi. And the cosine of pi is -1, so that's an easy one. And so we would have the -2, we're not going to forget it this time. We got f double prime of, we said we were going to choose pi. And so that's going to give us the -2 times -1, which is a +1, +2. It's positive, so it's concave. Good. Okay. And then in the next interval, we have from 3 pi over 2 to 2 pi. And what's something we've got memorized in there? Well, we like that pi over 3, right? So we could say this is 6 pi over 3. One less than that would be 5 pi over 3. And cosine is positive there. So we know that the cosine of pi over 3 is a half. So we reference back to that half. It's in quadrant 4 where cosine is positive. So we have positive a half. We still have times that -2. So f double prime of 5 pi over 3 was a -2 times a +1/2, which gives me a -1. So it's concave down. Okay. Now, from in this, at this place, pi over 2, we went from a concave down, right, to a concave up. Therefore, at that point, there must be a point of inflection because it changed concavity there. Went from a concave down to a concave up. In this next section over here at 3 pi over 2, it went from a concave up to a concave down. So there must have been a point of inflection there. So we found where the second derivative was 0, which is possible points of inflection. We have to verify that it is a point of inflection by verifying that there's a change in concavity. There was a change in concavity at both points. So we say that we have 2 points of inflection. The one point is pi over 2 something, and the other one is 3 pi over 2 something, and we have to find the y's that go with those x's because it wanted us to name the point of inflection, so we've got a little bit more work to do. Now, to find the y of the point, where do we plug that x?
To your original function.
Into the original function. I'm going to get rid of some of this. So we've got to take those values and plug them into our original function to get the y values that go with them. So we're plugging back in up here. So if we do f of pi over 2, we will have pi over 2 plus 2 cosine pi over 2, which is going to be pi over 2 plus 2 times, what's the cosine of pi over 2? 0. And so we're going to have pi over 2. Okay. And then we need to find the y value, the function value that goes with 3 pi over 2. So we want f of 3 pi over 2, which is going to be 3 pi over 2 plus 2 times the cosine of 3 pi over 2. And so we have 3 pi over 2 plus 2 times 0 again, which gives us 3 pi over 2. So we investigated the test points. We looked at concavity. That verified to us that at both of those test points there was a change in concavity, therefore they're both points of inflection. We needed to get the y of the points. We went back to the original function with our test points and got their y values. Any questions on number 6? Okay. Number 7. Number 7 says find all relative extrema. Use the second derivative test where applicable. Use the second derivative test where applicable. Now what's that? What's it? What can we do there? Let's talk about this again. Okay? If we were to do the first derivative, what do we know about first derivative? First of all, what is it? What's the definition of that? It is the slope of the tangent line at any point. Now that's the very beginning. Now if we set that equal to 0, then what are you visualizing? You've got to be visualizing that you have the slope of a horizontal line is 0, right? Or you're visualizing this, or you're visualizing that one of the inflection, you see. Okay, now, right here, the slope is positive, 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 negative, 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 0, right? Slope is positive, slope is negative, slope is 0. Right here, slope is negative, slope is positive, slope is 0. Right here, slope is positive, slope is positive, slope is 0. So with the first derivative test, if it goes from positive to negative, then at that critical point, there is a maximum. Okay? With the first derivative test, if it goes from negative to positive, at that critical point, there's a minimum. In the first derivative test, if it goes from positive to positive or negative to negative, it's continually increasing, then there's a change in concavity there, therefore there's a point of inflection. So how could we take these critical numbers? These would be our critical numbers, right? Could we take those critical numbers and plug them into the second derivative to find out anything? We've usually plugged our critical numbers back, found the intervals in the first derivative, and we took our test points from our second derivative and we found intervals in the second derivative. But could we take the critical numbers from the first derivative and plug them into the second derivative and learn anything? Let's think about that. What if I took that point and plugged it into the second derivative? What would I find out about that point? It's a part of a concave band. Right? What if I took this point and I plugged it into the second derivative? It's going to be a part of a concave up. In other words, the second derivative is going to be positive at that critical point. And here, the second derivative is going to be, I got those backwards. At this point, the second derivative will be negative, and so it's concave down. At this point, the second derivative would be positive, so it's concave up. At this point over here, what would be true at the second derivative? It's a point of inflection. So what would actually be happening in the second derivative at that very point? It would be zero, you see. At that one point, what's true? The first derivative and the second derivative at a point of inflection are both zero. Now, if the second derivative is zero but not the first, so when we do the second derivative and we find a zero, we think, well, that's a possible point of inflection, but it may not be a point of inflection. But if it's a critical number and the test point, see, then it's going to lock it. So what we can do to determine the relative extrema using the second derivative test is we can just say, well, let's find our critical numbers and let's plug them into the second derivative. Let's find our critical numbers, plug them into the second derivative, and if in the second derivative the critical number gives you a negative value, then we know it's concave down at that point. Therefore, at that point, it must be a relative max. Because first derivative says it's either a relative max, relative min, or point of inflection. If we take a critical number and we plug it into the second derivative and it comes out to be positive, we know that that thing is concave up. So at that critical number, since it's concave up, then there must be a relative minimum. And then if at that critical number the second derivative is zero, that means at that point it's neither concave up or concave down. So there must have been a change in concavity at that point. Therefore, it must be a point of inflection. Okay? Hopefully we made that make sense and said all that right. It gets a little confusing because we've been sticking critical numbers and looking at those from the standpoint of first derivative. And then we looked at test numbers from the standpoint of second derivative. Now we're taking our critical numbers and looking at them in the second derivative. So we've kind of changed the way we're playing the game. Okay, so here we go. We've got f prime of x, f prime of x. We're doing this to get our critical numbers. And we would have 3x squared minus 6x. There's our first derivative. Now, we actually want to get our critical numbers, okay? So we're going to say 3x squared minus 6x equals 0. And we're going to find the zeros of that quadratic. To do that, we can factor out a 3x, and we have 3x times x minus 2 equals 0. Agree so far? So if we set those equal to 0, we know this would give us a factor of 0. 3x equals 0, so x equals 0. X minus 2 equals 0, so x is equal to 2. So we have critical numbers coming out of our first derivative idea at 0 and 2. So we know our test intervals would be negative infinity to 0, but we're not going to do test intervals. We're actually going to go ahead and get the second derivative, and we're going to plug those critical numbers in there. So we're thinking at 0, there's either a relative max, relative min, or point of inflection. At 2, there's either a relative max, relative min, or point of inflection. And we're going to find that out by plugging those critical numbers into the second derivative. So we need to take the second derivative, and we're going to be looking at this to get our second derivative. So second derivative of that would be 6x minus 6. So there's our second derivative function. So what we want to do is see what's happening in the second derivative at our critical numbers that came out of our first derivative. So we're going to say, okay, let's take a look at f double prime of 0 and f double prime of 2. If we plug in a 0 for x in the second derivative with that critical number from the first derivative, we're going to get a -6. It's negative in the second derivative, which means at that point it is concave down. Which means at that point what?
That can be a possible.
Okay, so let's go back. That's right. We did the first derivative. We set it equal to 0, and we found possible max, mins, or points of inflection, critical numbers. We did the second derivative. We plugged the 0 into the second derivative function. It's negative, which tells us it's concave down. Because in the second derivative it's concave down, that tells me that at that point, that critical point, because it's concave down, it must have been a relative maximum. Okay? Relative max. Okay, you understand? Maybe I should. Okay. Now, when we plug in our other critical number, we're going to take this other critical number of 2. We're going to plug it into the second derivative. And so when we plug in a 2, we would have 6 times 2 is 12, and 12 minus 6 is 6, which is positive, which means that it is concave up. And if the second derivative is positive and it's concave up, it means that that point was in a situation like that. Therefore, at that point, there is a relative minimum. All right. Any questions on that? Now, we still need to find those function values, right? So we're going to say there's a relative maximum at 0 something. And there's a relative minimum at 2 something, right? And to get those somethings, we have to plug those back into the original function. So when we put in a 0 here, we're going to have f of 0 is 0 cubed minus 3 times 0 squared plus 3, which is 3. So my relative maximum is at 0, 3. And my relative minimum, we need to find the function value at 2. So we would have 2 cubed minus 3 times 2 squared plus 3, which is going to give us 8 minus 12 is negative 4 plus 3 is negative 1. We just might want to check that out. Negative 1, that is correct. And so we have a relative maximum at 0, 3 and a relative minimum at 2, negative 1. All right. Any questions on that? That got a little harder for me to, when I first started doing it, because we were using all of the critical number ideas the first derivative, and then we were using all the test number ideas the second derivative. And on this, we took those first derivative critical numbers and put them into the second derivative. And we kind of shortcutted the whole process. Okay? Any questions on number 7? All right.